Okay, so thanks everyone for showing up in those crazy days. And also I want to thank the committee. So Roneh and Shimon, Danny, thank you. Thank you for doing this. Thanks for the flexibility. But most of all, special thanks is to my advisor, Michal. I think none of the works that you're about to see now would have been possible without her. So I'm very grateful for having the chance working with her. And in this talk today, so I'll talk about this thing we've been doing for the last couple of years called deep internal learning. And if we're good with the times, then this plus over here, we can maybe cover some more other things. We'll see about this. Let's talk about patches and small ones, especially. So small patches recur inside natural images. And this looks like a contrived example. This is a toy example. I'm talking about actually smaller patches than what you see here, and the evidence is overwhelming for this prior as a phenomenon. And it's to the extent that it was used for countless works solving a lot of challenges, some very famous non-local means and BM3D, and many more. And it turns out that patches also recur across different scales of a single image. So that if we have some patch here, we're going to find this counterpart in a smaller scale of the image. And this was used a lot too, actually as far back as the 80s for things like fractal compression and super resolution, a lot in our lab. And the great thing about this approach in general is that it is totally unsupervised, doesn't require any additional data, anything else. But then in 2012 happened this thing that deep learning came around, and slowly but surely every type of challenge, actually deep learning outperformed these existing methods. And this brought us to where we were, I'd say about 4.5 years ago. I needed to find a research topic. So I met with Michal, and we needed to decide what we're going to do. And Michal suggested we do this, try to combine deep learning with these things we know about internal statistics. And I said, great, that sounds like a very good idea, but I have some more other ideas. And I specifically remember that we had 12 of these ideas. So Michal said, okay, we need to decide. I asked, how much time do I have to decide? And Michal was actually great about this. So she said, take all the time you need. And then choose number one. So this is how probably everything started. And what we came up with was that we want to take the power of deep learning and combine it with the power of internal statistics to this thing we call deep internal learning. And the main thing we do is that we train an image-specific convnet, and we do it at test time and on the test image only. Now, how can you train a network just on a single image? So we're working with fully convolutional networks, and the thing about fully conv is that it's actually like learning from a bag of patches, because each output you get is just a function of its receptive field, and every one of them is separately so. And if you pay attention, you'll see that the number of patches inside a single image, if you take away boundary effects, is actually the number of pixels in an image. So we're talking about hundreds of thousands, maybe millions. So this is a lot of data. And what you can actually say is that you're actually training on this huge batch of patches. So you have enough data just in one single image. And the first work for which we demonstrated this principle was for the challenge of super resolution. And let me just describe very briefly how deep super resolution usually works. So what you have is these low resolution images, and you feed them to this usually big network, and you train it with the labels that are the high resolution counterparts, and you train it for hours or days or whatever time needed, and you would usually get really nice results. There is an endless amount of work doing exactly this. However, they tend to suffer from some very important major problems. So the first thing is that they're only trained for this one specific downscaling method. So the low resolution data was actually created from the high resolution data synthetically. It was somehow downscaled. And a network is only trained to undo this specific downscaling. The second thing is that it cannot handle any artifacts. So if you have noise or blur, these networks, they just produce meaningless results. The third is that they're only applicable to the data they were trained on. So most of these networks, they're trained on natural images. But what if you wanted to have a different type of data? For example, what if you have microscopy data or from a telescope or whatever? These would simply be not applicable. And lastly, they're only good for specific scales. So you have a network trained for a factor of 2, for a factor of 4, 8, whatever. But what if I now want to do super resolution vertically 3.2 and horizontally 4.7? This wouldn't be usually possible with these networks. So we came up with this thing called zero-shot super resolution, ZSSR for short. And the idea, remember that what we're going to do is to train a network on a single image. So what we're doing is this: we'll take the image, and now we're going to do the counterintuitive thing, and we're actually going to downscale it. So now we have the low resolution, and we're going to feed it to this network and train. This is a very small, fully convolutional network. It trains very fast. So it took us 9 seconds on a V100 GPU. And now we feed it and we get what we're hoping is the super resolution of the low resolution of I. And to make sure that indeed this is what we get, we're going to use this autoencoder-like loss, so that we're simply trying to reconstruct the original image from the low resolution image. Now, once this thing is trained, once this thing is trained, I'm now able to take this network and now apply it to the original input image to get the super resolution that I wanted to get. Now, why would that thing work? What would it fit to the original input image? So keep in mind that this is a fully convolutional network, and as such, it actually trains on patches. Okay, it trains on patches from this low resolution image. And if it knows how to super resolve patches from this low resolution image, and we believe this thing saying that we have the same distribution of patches in the low resolution image and in the original image, this means that the same network is actually also trained to super resolve patches from the original image. Now, apparently, internal overfitting is a thing. So if we want to maximize our results and not suffer a bit from overfitting, so we're actually not going to train just on the original image, we're going to use augmentations. So we flip, rotate, whatever, and this actually improves the results. Now, one thing we didn't discuss, which is actually very important, is this downscaling over here. So I mentioned before that it's very important the way you downscale your low resolution data. You need to downscale it correctly, as the image you have was downscaled from this non-available high resolution counterpart. So this can be done by various ways. So either you know it by some kind of an oracle, so I don't know, camera specs or whatever. And at the time we used this great work called Blind Super Resolution by Tomer Michaeli and Michal a few years ago to estimate the kernel. And in a few minutes, I'll show you a great way that, that we have for this estimation of the downscaling process. I'm going to show just very few results so that we can have good, make it on time. So here's an input image. That's checkpoint Charlie in Berlin, an old photo. And if we use this standard super resolution, it's called EDSR. It's like almost this state of the art now for external train. This is what you get. But if we actually use our ZSSR, so you can see the differences are quite big. And if we even zoom in more, then you can see we get much more details. This is a true super resolution. Take a look at this gap between these guys' legs over here. Here's another one, and this was downscaled from with an unknown kernel, unknown to the algorithm. But for us, we know now that this is the true kernel it was downscaled by. And for those of you who don't know, this is how the ideal assumed by cubic kernel looks like. And we estimated. So before estimating the kernel, let's see the result of this EDSR plus. This is standard external super resolution network. This is how it looks like. And we estimated the kernel with this blind SR method. And you can see the estimation is not perfect. It's not the correct kernel, but it's close enough. And then we use this with ZSSR, and you can see that the difference is quite huge. You can see a lot of details that are very blurry when trained externally. So this brings us,
in principle, in the other methods that use the database, you could use like a latent variable or an additional vector of variables that give you the kernel, and then train those systems to deal with unknown kernels.
Yeah, so
can you comment on that?
Yeah, I'll briefly comment that you can. There are many things you can do. Today there are a lot of really great methods for blind super resolution. But the naive way of just training, using a random kernel at each time, this doesn't work. This was actually tried, and the experiment exists in paper one of these blind methods. You can do more sophisticated things with decoding the kernel and other stuff that today people are doing successfully. Yeah. Okay, so this brings us to the next work, and the place we were is that okay, we can use this deep internal learning thing for super resolution, but we really wanted to do some more other stuff, some other computer vision tasks. So together with Yossi, we came up with this very important observation, saying that many seemingly unrelated computer vision tasks actually can be put under the same umbrella of this thing called image layer decomposition. And it's best explained by example. So you can see this zebra over here. What if I can somehow decompose it? And I'll decompose it such that I have some kind of mask multiplied by this zebra pattern, plus the anti-mask multiplied by the background pattern. So if I'm able to do such decomposition, I'm actually able to do segmentation, because this mask here is the segmentation of the zebra. And very similarly, I can go about dehazing, so that I have the haze-free image multiplied by the thing called transmission map, and the anti-map multiplied by the thing called the air light. But here I have, if I am able to do such decomposition, now I have the haze-free image. And very similarly, also the situations like when you take a picture through a window and you have this transparency situation and you want to decompose the transmission and the reflection. So we build upon this thing that I'm sure some of you at least familiar with. It's called deep image wire. And they were showing this thing that they simply take a network, a fully convolutional network with static noise as input, and they train it just to overfit this one single image. This is all that they're doing now, and this is a very easy task. So they're able to reconstruct this image quite easily. And they show many really cool things, but one important thing that I want to talk about that they're showing is that what if the image that I'm trying to overfit to is a noisy image? And what they're doing now is they're not going to train it all the way. They're going to stop at some intermediate iteration. And surprisingly, what you're going to get is sort of the clean image if you stop just like right in the right time. So the noise only comes later in the optimization. And here is our interpretation for why this thing happens. So in this natural image, you have low patch entropy. You have similarity between many patches. This is as opposed to the noisy image. So if you take two similar patches, you can see they're very similar to each other. But these two patches, if you take them from the noisy image, they're not that similar anymore. So it's much harder for a fully convolutional network that is based on this thing that at every location it acts the same. It's harder and takes more time to generate the more complicated, the higher entropy. And there are many views you can look at it. Also a higher frequency. Okay, the less correlation you have between patches, the longer it takes the network to train to be able to generate it. So here's what we're doing with this observation. So we're going to take two of these networks, okay? And hence the name double deep. Deep stands for deep image prior. So we take two of them, and now we're going to sum the results. And we're going to train this whole thing together and try to overfit to some mixed image. And again, this is a very easy task to do. But here's where the magic happens. So naturally, what's going to happen now is that at each side of the double dip, we're going to get one of the layers that we're trying to decompose. Now, we're helping it a little bit with this thing called exclusion loss, but the main thing happened naturally. And again, the reason is that each dip on its own is converging to the easiest solution. The most natural solution is the one where there is the highest correlation between different patches, where there are the lowest frequencies. And this is actually happening naturally, just with a little push there with the exclusion loss. Now, we don't actually have to do just this straightforward summation. We can use a mask, and the mask can be learned. And now when we're using the mask, the thing is that the regularization that we apply to this mask is actually going to determine the type of task that we're performing now. So, for example, what if I encourage this mask to be binary? So I can use it for image segmentation now. So having this zebra over here, I'm going to train this thing again. But now the mask, which is also learned and is encouraged to be binary, now it's going to converge to the segmentation mask. And at each side, I'm going to get either zebra pattern or background pattern. And from all this thing, I can take this mask as the final result for image segmentation. And it turns out that we were able to do quite a lot of applications using this. So here are some examples for image segmentation. And this is not semantic segmentation and certainly not state-of-the-art segmentation, but it's quite impressive what you can do just with a single image and not even a clue of what this segmentation should look like. You see, some are really non-trivial here. And for dehazing, we were actually able to get, at the time at least, results that were state-of-the-art. We got really, really nice results cleaning this haze from images, and we could also recover this transmission map. And I'm going to rush through some of these results so that we can make it. I'll say something about watermark removal. So there are these images protected by user rights. So this is a bit malicious, but actually you can look at it as two layers. So one layer is the original image, and the second layer is this watermark, and we're able to separate them. And we do some for video, not as perfect as for the images, but still possible. And okay, so we were doing all these nice things using deep internal learning, and now everybody were talking about GANs, and we wanted some too. So we were thinking about this is together with the Shai and with Philip, and we were trying to do this thing called an internal GAN. And let me explain what an internal GAN is. So as most of you know, a regular GAN trains on this collection of images, and then once trained is able to generate images from the same distribution of images. On the other hand, an internal GAN trains just on a single image, And you have to remember that a single image actually is a huge collection of patches, sometimes hundreds of thousands or millions. So we're able to train this GAN. And what do we expect to get? So we want to create a new image of a different shape, but that consists of the same patch distribution. So this is a thing that can look, for example, like this. So you see, this is a bigger image, but it's not just stretched. It uses the same small patches that we have in this image here. So it has more windows and more bars in the barn in the back here, and another tiny barn was created there. You can go to the other direction, and this is sort of a visual summary. Okay, so you have this a smaller image, but looks very realistic, and all the elements are in the same size that we have in the original image. We just have less windows and less bars and less other stuff in the image. So how do you go about doing this one? So say we have this input image. We're going to feed it together with a transformation that determines the way we want to change the image. And we're going to feed it to a generator that we hope that will generate this retargeted image. And we have all these examples that can be fake examples for a discriminator. And this discriminator has many fake examples, but it only has one real example, which is the original input image. So the discriminator is actually trying to judge whether what it sees is from the original image or the retargeted one. But the way it does so is not just with a single scalar. So the discriminator is fully convolutional, and it returns this map, map saying for every patch to what extent it believes that this patch came from the original input image. And so the generator's job is trying to fool the discriminator to generate an image a different size, but that all of its patches look like they came from the original input image. Now, again, apparently internal mode collapse is a thing. So what if, for example, we generate this image that consists only of this grass? So the discriminator has no problem with this because all of these are valid patches. So what we do to solve this is we take the generated image and we put it again inside the generator. Only this time we're using the inverse of the transformation that we originally used. And we're basically trying to reconstruct with this simple L1 loss to reconstruct the original image. And this means that we cannot lose any information in the way because we won't be able to do this cycle loss. So the final loss we have is the GAN loss together with this reconstruction loss. So let's see how this looks like, what this thing does. So here is one result that we have. So you can see these corn cobs over here. And what if I try to enlarge this in the vertical dimension? So you can see that the image you get is not just stretched. Okay, we get more corn seeds. And we can also do it in the vertical dimension. And what's interesting about this is that no two corn cobs are alike. Okay, so it's as if behind the scenes there is this implicit corn cob distribution that generates corn cobs, which in turn consist of this implicit corn seed distribution. They can be either yellow, white, different sizes, but all match with these overlappings. And since a neural network is a continuous function, we're able to just modify the transformation and produce these nice videos showing this morphing. And let me show some more results. So here is a result we like. So you can see that this fruit stand is now changing its size extremely even, and it's not stretched. So either it's fruits being added and removed, or new boxes of fruits are added and removed. And we don't actually have to just do resizing. So we can do other transformations. So for example, we can do affine transformation or even just general homographies. And whatever we do, the elements inside the image maintain their original shape and size, even though the image changes. So here are some more results. You can see that no penguin is getting fatter, just more penguins are added or removed. But actually, nobody is perfect, right? Because InGAN doesn't know anything about semantics. It doesn't know anything about objects or scenes. So this is a perfectly good solution when trying to enlarge this image here. And I've been asked about this work SynGAN, and I believe most of you are aware of it. So Tamar and Tali and Tomer, they have this really great work, and they're doing things that kind of sound similar to what I just showed you. They're doing these new instances of images using a single image, and they even got the best paper award for this in ICCV for this work. And I've been asked a lot, what's the difference between InGAN and SynGAN? And the short answer is that InGAN is just like SynGAN, only that it got its S kicked. Okay, so but this is just joking. The main differences are that for InGAN the input is an image, whereas in SynGAN the input is noise and you generate from noise. And in InGAN we do this retargeting, so we enforce this completeness term, so that we want everything that we had in the original image to remain in the generated image. And for SynGAN, they have these many cool apps that they're doing using this architecture they have there.
Assaf?
Right. Yeah.
Assaf, yes. I want to ask about the inverse GAN. Is it deterministically determined by the forward GAN, or is it, or does it have free parameters that you train?
Okay, so this is just another instance of the exact same generator. So these are the same parameters. Okay. It's shared weights. Okay, the only thing different is the transformation. So it's like the input is different, and the transformation is different. Okay, but these are shared weights.
רונן, זה אותו encoder.
So how does it encode the distribution of the output image? It's a different distribution. I mean, you want them to be the same.
So the parameters are the same, and the generator doesn't exactly encode distribution. I would say that the generator receives an image as an input. So the generator encodes, I would say that the question the generator answers is, how do I transform the image but preserve the distribution of patches? So it's different from when you just input noise and generate something. It's more like a conditional generation.
Yeah, but you overfit to the image, which means in a sense that you overfit it to a specific distribution.
Right, but it's the same
input.
Right,
but not. The thing you want is to judge that it's the same distribution. You're not guaranteed to have the same distribution.
Right, so for this inverse activation of the generator, I'm not using a discriminator to judge the distribution. Rather, I'm using just simple L1 loss, because you know exactly what you want there. Okay, so instead of saying I want this to be some distribution, I'm saying I want this exact specific result, which consists by accident by patches that belong to the distribution that I'm interested in. But in this case, I'm fortunate enough to be able to optimize it for a specific output and not just for this general distribution. Okay, so at this point, we had this thing that we were doing for a lot of understandings about super resolution, and we were able to do these internal GANs, and we figured out that we're able to combine both of these and to solve a problem which is much harder in this world of super resolution. And this is together with Sefi Belkligler. And first we need to somehow understand what is exactly super resolution. So each low resolution image that we want to super resolve was created from a high resolution image. And the way it was created is by this weighted average of the pixels in the high resolution image in matching locations. And this actually means that we generate the low resolution image by a convolution with the high resolution image and subsampling. And the convolution is with some kernel, and here are some examples for what this kernel can look like. And the thing is that this kernel is extremely important. So if you do super resolution and assume the wrong kernel, you're not going to get anything that makes sense. You might as well just do interpolation. Super resolution cannot work assuming the wrong kernel. So this raises the much harder problem called blind super resolution, which is also the relevant problem, because all these networks doing super resolution assuming bicubic downscaling, they're not actually practical for anything meaningful. They're networks that are good for super resolution challenges. A picture you take with your camera, picture that you get by accident from a variety of sources, you do not know the downscaling kernel that matches them. So real super resolution is blind super resolution. This is a much more interesting and much harder challenge. So what do we know if we get an image and we want to know what the correct super resolution kernel is? So let's say I have this input image that I want to super resolve. This means that if I super resolve it, there is a connection going the other way of convolution and subsampling to create the low resolution image from the high resolution one. And again, I'm going to this work by Tomer Michaeli and by Michal, 2013. And they had this very important observation saying that the correct super resolution kernel is the one that maximizes the recurrence of patches across different scales of the image. So if you downscale the image you have using the correct kernel, you expect to maximize the recurrence of patches between those two images. And this is a very important observation. And we tackled it using this approach of internal GAN. So by now we know about internal GANs and what they can do. So here is how this thing called Kernel Gan works. So we have this input image that we want to eventually super resolve, but right now we want to estimate its downscaling kernel. So I'm going to use this generator that does downscaling to get a downscaled image. And remember that what I want is that the patch distribution of the downscaled image is going to be as similar as possible to the patch distribution of the original input image. And to make sure that it does, I'm going to use a discriminator. Again, it's a fully convolutional discriminator, and it either gets a crop from the downscaled image or a crop from the original input image, and it needs to decide whether the patches it sees actually came from the downscaled image or from the original one. And this means that the generator's job is try to fool the discriminator that the downscaled image consists of patches that actually belong to the original input image. Now, once this thing is trained, the generator actually is actually now the correct downscaling process. So I can use this as the downscaling kernel. Now we need to think what kind of a model we want to use for the generator. And usually what you do is you use these big neural networks to do so. But if we do this, then there is no constraint saying that this process needs to be linear or it needs to be to act as a downscaling or something that makes sense. So for example, it can do just fill this image all with the same patch, which is a valid patch, and everything will be okay. But this certainly is not what we're looking for. We need to remember that we're looking for something much simpler. We want this to be this linear process of convolution and subsampling. Now, in deep learning terms, convolution and subsampling is simply a single striated convolutional layer. Yeah.
Can I ask a question about the previous slide?
Yeah.
So what is the intuition for discriminator to discriminate between crops and not between patches like before?
No, it's between patches. The crops actually make no difference. You could have taken the entire image. The reason we're using crops is just that we'll have the same size for the fake image and for the real image.
Oh, okay, but it's still a patch discriminator.
Patches, you have this real fake map here.
Mm-hmm. Okay, thanks.
Okay, so in deep learning terms, convolution and subsampling is nothing but a single sprited convolutional layer. So, okay, so this is something we can work with. We can take this single layer and use it inside this kernel GAN architecture that you've just seen. And indeed, we tried this thing. So we took a bunch of images and a bunch of kernels, ground truth kernels that we know, and we applied kernel GAN and we let it converge. And we were sure this is going to work now. And what we're getting is very bad results, horrible results that don't look anything like the kernels that we wanted to get. And it took us quite a while to figure out what's going on here. And we came up with this following hypothesis. So the basic paradigm in optimization of deep networks is that there are no bad local minima. So everyone's saying this thing that the optimization surface looks like this egg carton, and whatever local minimum you get to, with very, very high probability, it's a good local minimum, it's a good solution. The problem is that in our case, we have this linear model followed by a highly non-convex loss. The discriminator is sort of a loss, which is very non-convex. And we know it for a fact that there is a single correct solution, which is the correct kernel, the ground truth kernel. And whatever, if we start from this random initialization, then the chances for us to get to this specific global minimum are actually close to zero. So this is why we were not able to converge to the correct kernel that we wanted. So we cannot use this thing. And the truth is that at this point, we sort of killed the project. So this project was dead for a month, I think. Until just unrelatedly, someday, unrelatedly, I got to talk on the phone with Nadav Cohen. Nadav Cohen today in Tel Aviv University, back then used to be at IAS Princeton. And he was just mentioning that he's studying this thing called deep linear networks. And deep linear networks is exactly what it sounds like. It's deep networks that have no non-linearities. And I won't lie to you. At first, I thought this is the stupidest thing I've ever heard, because a deep linear network is just equivalent to a single linear layer, because you just multiply all these matrices together and you get just one single matrix. Why would you do that? And it's true that in terms of expressivity, but in terms of optimization, things are a bit different. So sure, you multiply all of these and you get this one single kernel, assuming they're all convolution layers. You get this one single kernel that is equivalent to all this multiplication. But in optimization term, say that we have on the right side of this equation, say that we have the correct kernel. We have exactly what we want to get, the correct set of weights for this kernel. So in the right side of the equation, we only have one possible solution if we optimize over this. But think about it, that the left side of this equation has infinitely many factorizations, possible factorization for this one matrix over here, okay? So once you have infinitely many such decompositions, and you can see that if you multiply some layer by a matrix and then the inverse of this matrix, it stays the same. So now we have infinitely many good minima. And now this optimization process can actually converge to a good local minimum point. And indeed, look again at this experiment that we did. So we have these ground truth kernels, and this is the horrible results we got before. And this is what we get now. You can see that now we're getting somewhere, right? Now we're getting kernels that look very similar to where we want to get. And I should also mention that this is the first practical use of deep linear networks. So everybody was doing like this theory stuff with linear networks, but as far as we know, this is the first time that it was used for something that is more than that, it is a practical thing. And I'm going to show just one result so that we can see more stuff. So we compared to this thing called PDN. It was the leader in blind super resolution. It won the challenge, this thing called entire challenge. And you can see when we compare that, when we use our estimated kernel plus ZSSR that I showed you before, we're getting results that are, I think, much better. You can see in the sleeve of this woman here, or look at her lips or her eye, you get much more details and far better results.
Assaf, it only now started.
Oh, so You see it a bit late? Okay, I see it kind of jiggles funny. Okay, but I hope you can see it. There is some latency with this GIF. Okay. So now for a thing that is a bit different. And this is a paper called Drop the GAN. It's together with Niv Granot and with Ben Feinstein and with Shai. And the first thing that everybody is saying to me when they hear about this paper is that it has a provocative title. So let me start by saying that we love GANs, okay? That there are great models that do incredible things and we're not against them at anything, okay? With that being said, I should also mention that training GANs is hard, okay? We have tons of problems when we're trying to train GANs. Here are just a few of them. So it has like a really, really long training time, and it suffers from these crazy things like mode collapse, and it's unstable, and you have this regression, and you eventually see these artifacts. Okay. So the way things turned out to be was that Niv Granot was trying to do this alternative generative model. And at the time, we were using this VQ-VAE. It's this code book and this nearest embedding thing in the middle. And we were getting some interesting things. But slowly, we figured out that not everything we're using is actually necessary. So we started stripping off things like the losses and then all these and the weights in the neural networks here and the code book. And we found ourselves left just with this nearest neighbor thing, and that we're still able to do these relatively nice things, like when you have some input image and you can generate this variety of instances that consist of the same patch distribution, but with different structure. This was quite surprising. And let me show you how this model works. But first I need to mention that doing patches nearest neighbors is nothing that we invented. So people were doing all sorts of manipulations to images using these methods. But what we're suggesting here is to cast this good old patch-based method as a generative model, as a model that receives noise and returns a generated image. And we put this on a GPU and make it very efficient. And let me show you how this thing works. So let's say I have this input image right here. So first we downscale it, and then we downscale it again and again and again until we have this image pyramid. And now what I'm going to do, I'm going to take this other pyramid, trying to reconstruct the image when I use this input noise. And at every floor of this reconstruction pyramid, I'm going to use this module we call PNN. This stands for patch nearest neighbor. So let's zoom in the PNN, okay, and see how it works. So the PNN receives three input images called query, key, and value, same as some of you are aware from attention mechanisms. Okay, we have the query, key, and value. And the first thing we do is we extract each such image to overlapping patches. Okay, so we have these patches. And now we're going to compute all the possible distances. So this is a huge matrix that takes every possible distance between every query patch and key patch that we have here. And what we're going to witness now is that, for example, some of the keys may have very large values. These are keys that are far away from all the possible queries. Whereas some other keys may all have small values. And this is especially what you see for smooth patches. So smooth patches like everybody, they're close enough to everybody. And this makes the game unfair. So if you just use it the way it is, what you're probably going to get when you try to generate a new instance of this image is just an image of a sky. No balloons, no ground, nothing, just sky, because these are the most common patches that you want to find. So what we did is we did this normalization so that every column you see here, every column of, for every key, we actually divide by the minimum value of this column. So we're sort of saying you're only close to someone relatively to how this key is close to its closest neighbor from the query. And we have this hyperparameter alpha, which controls this thing. And this is what determines the term called completeness. Completeness means how much from the original image you're going to have in the generated image. So the smaller alpha is, the stronger this normalization is, and you're going to get more completeness. Next, what we're going to do is just take the mean value from every row. So this is the nearest neighbor. For every query, we get the nearest key. And now we're going to do this replacement, which is very common for query key value. So every query has its key, and every key corresponds to a value. And we're going to replace every query by its matching value. And now we have these output patches. And the last thing we're going to do is to generate a new image out of them. So we take these overlappings and we average them to get this new image. Right? So this is what this module here, this PNN, does. And at first, what we're doing, so the query is going to be not just the noise. We're going to add the smallest image in the pyramid for it, and this helps us maintain this global structure. So if you have sky, the sky will be up and the ground will be down, and nothing is going to mix up. And we're going to use both for the key and the value. We're going to use this image right here, but this is the first floor. It's different from the other ones, and now I'm going to get some result that all consists of patches coming from this tiny image over here. All the patches here came from there, okay? And now I want to go up one level. So I'm going to upscale the result I have here, and I'm going to use another PNN. So naturally now the values are going to come from this image and the matching floor at the image pyramid, right? Because this is what I want to use. I want to use patches from here. But take a look at this input here. You can see how blurry it is, okay? So I don't want to search for nearest neighbors of query patches from here. I don't want to search for them in here, okay? Because if I do so, I'm probably not going to find the exact patches that I want to find. So so what we came up with was to actually go one floor down and upscale by interpolation the smaller image, and this is going to be the keys. So patches from here look for patches from here, and then are finally replaced by patches from here. Okay, and now we are able to get results, and we do the same at every floor. We can have many such levels in the pyramid until we get our final output, which is an image that all consists of patches that came from the original input image. So this is an image that all of its patches actually came from here. They're just organized differently. There are more of them or less of other ones of them. And this is called GPNN, Generative Patch Nearest Neighbor. And one thing to notice here is that there are no parameters, no deep learning, no weights, no training, nothing. This just happens on the spot, on the image that you want to do another instance of, to generate by reference of. And here are some results that we have, and specifically pointing to this mountain down here. And you can see that that we have these very clear, very nice, sharp-looking results and very realistic mountains. This is comparing, for example, to Singan over here, that you tend to get results that are more smudgy. And this is because Singan eventually is a neural network that does regression, and things like this can happen. And over here, what we're getting is just, we reconstruct it from original patches that are all sharp and crisp, and we just organize them differently, and it looks very realistic. Here's some more results. And I particularly like these birds over here. So at first glance, it seems like it's the same image, but if you look closely, you see that the birds are rearranged here. The ordering is different, and you have this red bird twice and whatever. But I think it's very impressive to see that even though this is a different image, the ordering is different, still it looks super realistic. If I look at this image, I would have thought that it is realistic. It's also funny to see this six-legged elephant over here, that while semantically we know shouldn't exist, still in terms of patches, you see how crispy clear and how high quality this image is. I would have believed that someone just was creative and created this statue with the thick legs. And we had all these bunch of really nice applications. So one of them is this retargeting thing. So we can take this tower that is familiar to all of you, I think, and start by just naive resize, and then we downscale it, and then we use this coarse to fine process that we have just seen before, and now we're able to get this really nice improved cyclotron for the Weizmann Institute. Another thing is called structural analogies. So in structural analogies, you have your input image A and the input image B, and you want to preserve the structure from one image with the content of the other one. So for example, we can take this snow image, we downscale it, and now we're going to feed it again to this coarse to fine PNN process. And now we're able to get the structure from the snow image, but the patch distribution is of input image B, this send thing. And we have really nice results for this that I want to show you. So the red arrow stands for structure, while the black arrow stands for, I would say, content or style or patches, whatever you want to call this. And you can see that we get a result that I think is very realistic. You can see it looks really sharp and believable, I would say. And we can do the other side too. So we get this control tower, which is a bit weird, I think, but still looks very realistic, and the image is very sharp. We've seen this example, but now we can see both sides. So you can see this looks super realistic and preserves the exact structure with the exact content and patches from the other image that we have. And this is called sketch to image. And I really like this result because it even takes the pic from this, I think it's a duck over here, and put it in both sides of the letter S. And for reference, we can compare, there is another work doing this called structural analogy thing. And I think we get results that are significantly better. You can see that for our competitors, you can see that we have a very smudgy, unclear result, sometimes noisy. And this S is practically just taking this black thing, put it on the stones right here. Okay, for us, it's much more realistic, and I think with the higher quality. One last thing that Niv came up with is called conditional inpainting. And this is just like inpainting, only the user gets to color the missing parts using whatever color he wants, and then it affects the way you're going to complete the missing pieces. So again, you downscale and you go through the coarse to fine process, and now you see where we used green color, now we edited in a tree, and for the black color, we have another bull in the field. Okay, so for the quantitative results, I'm not going to bore you going through this table, but I'm going to say that we checked for every possible measure that you can check. And the verdict is that for all measures, this also includes a user study of many types. We did it very extensively. And the verdict is that this GPNN thing outperforms SynGAN and the other GANs methods too, for structural analogies and whatever. So GPNN outperforms in all measures and by a very large margin. And specifically pay attention to the runtime here. So things that used to take more than an hour, we can now do just by 2 seconds. Okay, 1 hour to 2 seconds, and get much better results. So so this is for us a very exciting work. And in this subject, I want to let you have this sneak peek on a thing that is the work in progress now. So this is Niv Chaim, and he was asking, okay, but what about videos? What can we do with videos? And some of you may remember the last Israeli Independence Day.
Assaf, I just want to make you aware of the time. It's,
yeah, I'm just about, yeah. So, so some of you may remember the last Independence Day. They were doing this parade thing and for COVID vaccines, and this is the first vaccination, the second vaccination, but we were especially intrigued by this part over here. So this sort of reminds, you see this one morphing into two. This sort of reminds us the things you usually do with GANs when you morph MNIST digits. So in this example from 0 to 1, and we're asking, can we use space-time patches and this nearest neighbor approach and now generate this sort of thing, but instead of going from 1 to 2, we want to go from 0 to 1. And it turns out that we're able to do that using space-time patches, which is really cool. And not just this, so we're able to do this to all the possible digits. I think you see it with a bit of latency. I'm sorry for that. So once submitted, you're invited to check it out. And about this, I want to say it's not the only thing that we're doing. So it's going to also have HD video generation and video summarization. And I think the most overwhelming thing is the runtime again, because when we try to run the competitor thing, doing a video generation from a single video, it actually took 8 days for a single video to run. And what we're doing now, using some very intelligent optimizations. So what we're doing now takes us 18 seconds, so days to seconds, and so again we're very excited about this. And I see that I don't have time for the plus that I had there, so I'm going to skip through this Google thing. Sorry for that. I knew this would possibly happen.
I think it's a really nice work. So maybe you want to give it 5 minutes and.
So if it's okay, I can do this 5 minute thing. Okay. So I'm not skipping. I'm going back. And so what we were asking with some really great people at Google, we were trying to bridge the gap between generative models and discriminative classification network. And what we're after is saying, okay, this is a classification network, and we know that you can feed it with an image and get the class. But we want to invert this network, meaning that I'm looking at this layer over here. I want to ask the question, which other images create the same feature map in this ConvNet as the original input image that I have here? And I don't want just one single additional image. What I want is to explore through this subspace of possible images. I hope you see it morphing. Yeah, I think you do. So I want to explore through this subspace, and I don't want to do it just in this specific layer. I want to do this in this layer and all the other layers all the way to the class. And I also don't want any optimization process to take place. I want to do this in the single feed forward for whatever example that I have, and for every layer that I want. Just in real time, I want to be able to explore through this subspace of images. This is explainability of networks at its best, I think. So here is how we're doing it. So we have this pre-trained classifier. We're not training it, we're not touching it, but we do construct a generator which has this mirror-like architecture with respect to this image, to this, to this classifier. And we have these correspondences. So every layer in the classifier corresponds to a block in the generator. And for example, when we turn on the connection in this layer, we're going to get this image. And if we jiggle with the input noise of the generator, we're able to explore through this subspace. And if we turn on the connection in a deeper layer, then you can see that the modifications are greater, and we can do this all the way to the class label. The deeper you go, the bigger modifications you get. And the way we train this is by 3 losses. So the first loss is an adversarial loss. This makes sure that what we get is realistic. I should say that this is a restriction. We don't want just anything, any possible inputs to the network that gives the same feature map. We want only the realistic images that we input the network and get the same feature map. We have another thing I'm not going to talk about called diversity loss, and a very important thing, reconstruction loss or feature reconstruction loss. So the way it works is we take the generated image and we feed it again now to the classification network up until the relevant layer. And in the relevant layer, we want the distance between the feature map of the original image and the feature map of the generated image to be as close as possible. And this makes sure that we're doing something very close to having the same feature map for both of them. All right, a cool thing is that we don't have to use the same layer for the entire image. So for example, we can use this mask. And for this layer here, we use this mask. And for this layer, we use the anti-mask. And now when we jiggle the noise, we severely modify the background while the bush is hardly changed. And we have tons of applications I'm going to rush through. So you've seen this thing generate by reference is like the main thing that we do. You can see that in here, it even adds this motorcycle at some point. And we have this thing called image repainting. It's like inpainting, but instead of having missing information you want to fill, you just replace existing information. So you've seen this bush, but what if you have this hiking image of yours and you want to like change the view behind you to many options? You can do that. I'm rushing through some results. Here's another cool thing. So this is called semantic image composition. Let's say I want to put this church inside both of these scenes. Now, I don't care if it's going to look the same. What I want is to maintain the same semantic meaning, but I want it to match the scene. So when I do this, you can see that I'm able to get two entirely different buildings, but both of them are semantically, I would say, semantically called temples, and they match the scenes that they were implanted in. I'm going to rush through some other results. We do other really cool stuff. This is called relabeling. So we can take highway to a desert road and a mountain to a volcano. And this is it. I'm approaching the end. And I just want to summarize on a personal note and show the final results of my PhD, the most important ones. And I'm going to compare to the prior state of the art. So Shocher et al. 2015. Before I started this master and PhD, we had 0 children and infinitely many free time. And the current state of the art we have now is us 2021 with 2 children and 0 free time. And this is probably the biggest change, the most important result during this time. It was incredible, I don't know, 4.5 years. And a lot has happened. And I want to thank everybody that took part in anything that I was doing here. And it's life-changing experience, especially when you become from a kid to a father during this time. So it's a big thing. And that's it. Now I'm ready to take your questions, whatever questions you have, I'll be happy to answer.
So thank you, Assaf. We have time for maybe 1 or 2 questions because then we have to proceed with the in a more intimate form. But if people have any questions, please go ahead.
Yeah, I have a question regarding the kernel gun. So you used a linear network with, I suppose, several layers. An alternative to that would be to have one layer with many channels and then average through 1-by-1 convolution. And
you mean average? Average once? I mean,
so,
we do use 1-by-1 convolutions. So the architecture is you have the first layer is I believe it was 5-by-5, the second 3-by-3, and then we have 4 more layers of 1-by-1 convolution.
Yeah, but I'm saying just one layer with many channels. So then you have an overparameterized network as well, but you don't have depth. And in a sense, you take all these random solutions, random minima, and somehow by some kind of averaging, you try to get the global optimum. Did you try this?
No. So for this to work, would still be what we would be using would still be a deep linear network. It would have two layers, right? Because you need this hidden layer to have as many channels as you want. So what you're saying sounds like it could work. I mean, I think it's still like it's the same type of solution because you're not using a single layer now. You're using a network. You're just modifying the architecture. Like instead of depth, you're now using width, and this makes sense. I think this could work, but my guess is that it would be harder to optimize. The deeper the linear network is, so it turns out that it's easier to optimize. This also comes a bit from the theory, I think. And I should say one more thing about all this thing about this linear network and the reason why it works. I specifically said that it was a hypothesis. So we couldn't prove this. This was an intuition, and eventually empirically things work with it. But in no way I claim now that this was proved to be exactly what's happening there. Okay.
Any other questions?
I will be.
Go ahead.
I will be happy to ask a question. First, great talk, amazing results, really interesting. So referring to the first part of your talk, you've shown amazing super resolution image decomposition results, but to my understanding, everything is based on a single image. So you train on a single image and then you test on that image. So you may say, well, the super resolution is blind and everything is unsupervised, and that's right, but still it takes some time to train. So what if you would like to extend this and train a network to work for a set of images, not a single one? What would be the main limits to extend your work to do so?
Right. So first of all, I haven't noticed you're here, Tommy, and I'm very happy that you are. I am. Second, so the thing about this ZSSR thing is internal learning for a single image, and the desire to make it something that you can apply to many images exists for a long time, both for us and for others. So there are actually many attempts of doing so. Apparently, it's very popular in Korea, and there are several works from there, and they're using, for example, meta learning. So they have this network that is externally trained, but they use this meta learning thing so that in real time they can do this very fast fine tuning to a given image, and then have it have the best of both worlds. So this is one approach that you can do. And there are many other things, and I should say that lately, especially like in the last few months, there are amazing works for blind super resolution with super impressive results. Some of them even without estimating the kernel. But I do think that for me, at least, sort of a holy grail is doing this intelligent combination, as a general approach, an intelligent combination of external and internal training. I really feel that this should be like one of the most important things that we can do, like in this in relation to the modest thing that I'm dealing with.
Thanks.
Thanks.
Any other questions?
I'd like to ask a question. First of all, I'm also a big fan of your group's work. Very nice job. I wanted to ask about, I think it's regarding the ZSSR and Kernel Gan. regarding the recurrence of patches across scales. Do you think this can work also in non-natural image, like let's say drone or satellite images, in which the scales are relatively constant, if it's orthophotos?
So the short answer is yes. And this recurrence is, as I see it, is not a result of something in nature. This recurrence is as a result from the, I would say, the optical process that you're doing. So this thing happens in whatever type of image you get. I mean, if you generate random noise digitally with your computer, then sure, this wouldn't work. But everything that you capture through a camera and with the lens and and transform it to a digital image, then I'm pretty sure that it works. I didn't check every possible thing that exists, but for every type of data that is under these restrictions, then it would work. I'm not going to lay my entire philosophy for why it is so. We wouldn't have the time for that, but just as a short answer, so the answer is yes. Yeah.
Thanks.
Okay, I think we should wrap up this part, and maybe if the audience can now hang out and let the committee be left with Assaf, that would be nice. Thank you very much, everyone, and thank you, Assaf.
Thanks. 1 second back.